Okay, so the course is taking over from the slots which were being used for renewable energy physics, PHY 4815. So that's what we are taking over from until the end of the year. Is that clear? So I don't expect anything in terms of clashes. So since we are taking over from an existing course, are we clear? Hello?
Yes, it's clear.
Okay. The other thing is, from the timetable, I could only find 3 slots, but we need 4 slots, including one for the so-called tutorial. So where was the tutorial placed? Under what slot was the tutorial placed? When was the tutorial? When you're having your...
We placed the tutorial on Monday from 9 to 10.
From 9 to 10. Monday 9 to 10.
Yes, we used to have a tutorial from 9 to 10, then also on the lecture somewhere from 12 to 13.
Okay. Let me check Monday. Okay, so you're saying 9 to 10. Alright, that should be... Because I've got a class at 10 to 11. Then we meet again at 11. What was happening? Okay, fine. So we have a class on Monday, 12 to 13. Then there's another one. Okay, so I think we're also going to place it at 9 to 10. We don't have a lot of choice. So 9 to 10, that's where we're going to place, so that we have got 4 slots. The other thing is, most likely, I will not manage to... I don't know if I will manage to type or stuff like that, but most likely it's possible that I will not manage to do that. If I don't manage to do that, then I'll have to write the notes with pen and paper or with a pencil. Then I scan them. Then I upload them. Are we clear? So if you want to, if you don't like my handwriting, then you can write your stuff, the stuff in your own handwriting.
Your handwriting is just okay, so actually you should just be doing that.
If I can type, then we're going to type. I think because I'm just taking over this course, those I'm going to teach next year, probably they will have typed notes. Like I'm trying to work on typed notes for the PHY 3032. So those ones, I'm giving them typed notes since I already have stuff. For you guys, you have to do with handwritten notes. Okay. So now that we have sorted out the other slots, so that is Monday. So we'll meet twice on Monday. 40, 31, 09 to 10. Okay. The beginning of the course, the problem with this course is, I think also just generally the problem with the computational physics courses which you have is, it's not very clear what it is a person is supposed to teach you guys. Because the course outline is just not very useful. Okay, so as you can see, we will look at certain topics also which we looked at last time, but using a different method. And the other thing is, if we've already looked at a topic and I'm trying to introduce a method, we are not going to spend so much time on some of these things. Actually, I think going forward with any of these computational physics courses, if there is a method you're looking at, the most I'm going to do is just 2 examples. Okay, so if there's a derivation which you have to do, fine, we can do the derivation. Then after that, we can look at a few examples, 1 or 2 examples, which are suitable with that particular method. Not all methods are not all examples or questions are suitable for these things. So they're basically suitable for certain things. So we're going to look at some of that stuff. I will try to. The other week, I tried to create a rough outline of what we might have to do during the course. I'll try to work on. I'll scan it, then try to post it on the course. But this thing is not going to be final. I'll try to teach what I think is useful. Okay. So yeah. So I'll post something in terms of an outline. Then so that you can have an idea of what it is we are trying to do. But that's not going to be written in stone. Are we clear? If something better comes up, we might replace one particular thing with something else. Is that clear?
Yes, sir.
Yeah, so I'll post a rough outline of what we hope to accomplish between now and the end. And yeah, then that outline is also not going to be written in stone. Certain things might change depending on the ease with which it is to actually do certain things. And yeah, what I'm wondering here is what I have posted. Is it exactly what I wanted to post? It looks like I posted something which is more. Yeah. So I've posted something which is not the correct thing. So I need to stop. Oh, okay. Okay, so the first thing we've agreed on is on the Monday class, 9. The other thing we have to agree on is that our labs will have to take over the slot for numerical, for us is for renewable energy. The renewable energy physics labs are not done. Last week I had load shedding, so I don't know what we're going to do. There seems to be load shedding on Fridays in the place where I live. So there seems to be Friday load shedding. So if the load shedding on Friday continues this week, then we will have to find a different day for the lab. Are we clear? Yeah. So if I experience load shedding this Friday, then we have to find a different day for the lab. So with that bit, we have to wait and see. We need to do the labs for versus renewable energy. We need to finish. So that requires people to show up and participate. Then after that, you can write your stuff. Then you can give it to me, and we can mark it. Okay. So the method we want to look at today is what's referred to as, it's a bracketing method. Last time around, when you're doing computational physics, we looked at a bracketing method called bisection. This time around, we want to look at a bracketing method called a regular FOSI or force position method. It is a combination of something which looks like a bracketing method and something which looks like a second method. Okay, so what we have is the following. So we are with a function which is what's being represented by this line here. So this is our function, like that. So as you can see, clearly our function cuts the x-axis at this particular point here. So there is a root to this particular function. So what you're looking at, this method you're looking at is what is solutions to nonlinear equations using what's referred to as a force position method or regular forcing method. So with this bit, so we know that there is actually a root which exists at this particular point. Then this method is a bracketing method, but it's a modified bracketing method. So with like any other bracketing method, you choose your lower bracket. So in our case, if our lower bracket here is a, then the value of the function at a is f of a. That's what you have this side. Then our upper bracket is b, which we have here. Then the value of the function at b is f of b, this side. Okay, do you still remember what we did with bisection last year? Do you still have an idea? Hello? Do people still have an idea of what you did with bisection? Okay, I'm not receiving a response. All right, fine, I'll proceed. Okay, so the next thing you do is you connect this point, a comma f of a, this point here, you connect it with a line to this point here, f of b. This line, this dotted line. So you have this bit here, a comma f of a, then you've got this bit here, b comma f of b. So you connect these 2 points with this line. When you connect these 2 points with this line is going to cut the x-axis at this particular point, at x1. Is that clear? Can you see that the line cuts the x-axis at x1?
Yes, sir.
Yes, sir.
So you use your x1 as a solution. Okay? So you take your x1 to be a solution. So after you find it cuts the x-axis at x1, then you find out what is the value of the function at x1, which is what you have here, f of x1. So you get this point here. Then you connect this point with this one here. So you come up with this second line here. With this second line, when you do that, you connect your x1 point. It's going to give you another point here, which is x2. So your second line, your second chord, is going to cut the x-axis at x2. So your x2 is going to become your new solution. Is that clear? It's very simple and straightforward. So if your x2 becomes a new solution here, then you want to find out what is the value of the function at x2. The other thing you ask yourself is, what's the value of the function at x2, which is this, f of x2. So you keep on moving slowly, but surely you keep on moving closer and closer to what the actual root is supposed to be. So here at x2, f of x2, this is what you have, f of x2. Then you draw another line from f of x, from a, f of a, from there to this point here, which is f of x2 here, x2, f of x2 to this point here. When you draw that line, you notice that the line you've drawn is going to cut the x-axis at x3. Then after it cuts the line at x3, you find out what the value of the function is at f of x3, like that here. Then you draw another line from this point up to f of x3, like that. So you keep on slowly but surely. As long as you started with a bracket which is between a and B, slowly but surely you can clearly see that your root, your X values, they keep on moving towards what the actual value is supposed to be, where the root is here. So the distance between the successive between x1 and x2, okay, it's large. They need to keep on reducing and need to keep on shrinking, and you keep on doing that until it reaches some value you are happy with. So is the idea of this method clear to everyone, what it is you're trying to do? Is it clear?
It's clear, sir.
Okay, now the other thing is, we are not going to go around drawing, since we are doing a computational physics course, which means we have to come up with some program which is going to do this. We are not going to go around drawing these lines, okay? But we know that since it's a straight line, there is some equation of a straight line which you can use to connect this point, a and f of a, b and f of b, and there is this bit here, x1 and f of x1. So these points, these 3 points, you can come up with an equation of a straight line which is going to describe these 3 points. Okay, and that's what you're going to do. So we can see how all these 3 points, a, f of a, b, f of b, x1 and f of x1 are supposed to be related. Okay, so we have 2 points, a, f of a, which is this one here, and b, f of b, which is what we have here. These points have been connected by a straight line, so we know we can describe what a straight line is. We've been connected by the straight line, and they also pass through this point here, x1 and f of x1. So if you've got such a situation, then it's possible for you to describe the equation of a straight line given by this: y minus y1 divided by x minus x1 equals to y2 minus y1 divided by x1 minus x1. So in our case, our x1 y1 here, x1 y1, that's what's going to be this bit here, the b, x1 y1, because we want to come up with a slope which is positive, x1 y1, so it's going to be this part here. Our x2 y2 is going to be this bit here. Then this which is in the middle here, that's what's going to be our x and x1 and y. So our x1 y1, that's going to be our b and f of b. Our x2 y2, that's what we're going to take as our a and f of a. If we do that and substitute where we have got y2 and y1, where with y2 and y1 we put our f of a here, where with f of y2 we put our f of a, our y1 we put our f of b, our x2 here we put our a, our x1 we put our b there. So we're going to end up with what you have here. We're going to have f of b minus f of a minus f of b divided by a minus b. This other side, this bit here, we're going to have y minus y1. Y1 is our f of b, then x minus x1. Our x1 is just here, b. Okay, and this. So we have done the substitution. The only thing we're left with is this bit. You're left with the y and the x1. The y and the x1 in this case, with this formula, when you look at this, is basically the point where the whatever point you're interested in between these 2 points, a and b. So in this case, we're interested in x1. So our x is going to be x1. Our y is going to be f of 1. So that's what we end up having here at x comma y. So this is going to be our x1, and f of x1 equals that. So for this y here, we put our f of x1 for the x. We're going to put our x1 there. Okay. So the whole point here is for us to find a root. We want to find what's going to be f of x. Okay. Now at f of x, if we take f of x, if this is going to be our root, if x1 is going to be our root, our guess root, then it must be that f of x1 should be equals to 0, or approximately equals to 0. That's the only way x1 is. If we go around saying that x1 is going to be the root, if we put x1 in the function f, it should give us something which is equals to 0 or something which is close to 0. Are we clear? If we say x1 is the root or is the answer to this equation, then f of x1 is supposed to be equals to 0. If we say x2 is the root, then f of x2 is supposed to be equals to 0. If we say x3 is the root, then f of x3 is supposed to be equals to 0. Are we clear?
Yes, sir. Okay.
Yeah, that's what it means, really. So in this case, since we want to find x1 as our root, which is what you have here, we want to find x1 as a root, which is what you have here, then we set this thing, f of x1, to be approximately equals to 0 or just to be equals to 0. That's what we do here. So if x1 is our root, then f of x1 should be approximately equals to 0 or should be equals to 0. Do we agree with what you have done so far?
Yes.
So when you do this, when you set f of x1 to be equals to 0, so you put a 0 here. So you end up having a 0 here. 0 minus f of b divided by x1 minus b, which is equals to f of a minus f of b divided by a minus b. Okay. So that's going to, this 0 minus f of b, so you're going to end up with just a minus f of b divided by x1 minus b, which is equals to f of a minus f of b divided by a minus b. Okay. Next, we do a cross multiplication. We cross multiply on both sides. When you do a cross multiplication, so we multiply minus f of b times a minus b. That's what you end up having here, minus f of b multiplied by a minus b. And then this side, you have x1 minus b, which is what you have this side, x1 minus b multiplied by f of a minus f of b. So you have f of a minus f of b here. So you do cross multiplication, you end up with this expression. Then you expand that expression. When you expand this expression, so you end up having minus f of b times a. So you're going to end up with a minus f of b, then minus f of b multiplied by minus b. So you're going to end up with a minus b. Then inside here, there's minus f of b. Then this side, you have your f of a multiplied by x1. So you're going to end up with x1 f of a, then f of a multiplied by minus b. So you're going to end up with minus b f of a. Then you have what your minus f of b multiplied by x1. So you're going to end up with x1 f of b. Then you've got minus f of b multiplied by minus b. You're going to end up with minus b minus f of b. Is the multiplication clear here? The expansion?
Yes, sir.
Okay. Then we try to simplify this whole thing. When you try to do that, so you end up this a minus f of b. So that's it's going to give you minus a f of b. Then this one here minus b multiplied by minus f of b. So the minus and the minus, so you end up having a positive. So you end up with plus b f of b. So this minus and that minus, they will multiply. You end up having a positive. So you have minus f of a minus a f of b plus b f of b. That's going to be equals to what you have here, minus x1 f of b. So with x1 f of b, then minus b f of a. Okay, that's fine. Then you end up having the other one here, minus x1 f of b minus x1 f of b. Then this bit here, there is minus b here, there is a minus f of b here inside here. So there's a minus, and the minus, when you multiply, you end up having a plus. Is that clear? Okay, now if you look very carefully, there is this part here. There is b, f of b, this side. But there's also the same term appearing this side, b, f of b, this side. You see that?
Yes, sir.
Yeah, so we cancel that term, which is appearing on both sides. So when you cancel this term here, so this term, when you cancel it, so that's what we do here. We cancel the b, f of b. We also cancel this bit here, b, f of b. So when you cancel that, you're going to only remain with minus a, f of b. Then this side, you're going to remain with minus, you're going to remain with x1, f of a, minus b, f of a, then minus x1, f of b. So you have got this x1 here. There's a term, there are terms which contain x1, which is what you're interested in. So there's this term here. There's also this term which contains the x1. This other term which doesn't contain the x1, we take it to the other side. When we do that, we take this bit to the other side. We're going to end up with minus this bit, minus a, f of b, minus a, f of b, then plus what you have taken to the other side, which is this one here. So you're going to remain with, we're going to end up with plus b, f of a. That's going to be equals to x1, f of a, which is what you have here, then minus x1, f of b, which is what you have there. This side, there is x1, which is common. So we factor out when you factor out the x1, so you end up with x1 equals to bracket f of a minus f of b. So we can write, since we are looking for x1, we can write the whole thing so that we end up having on the other side, we end up with x1. So we end up with x1 equals to open bracket, square bracket, f of a minus f of b equals to what you have here, b f of a, b f of a minus a f of b. This bit. We have to remember what we have here. A is the lower bracket, b is the upper bracket, f of a is the value of the function at the lower bracket, f of b is the value of the function at the upper bracket. Okay, so we divide both sides using by this term. When you divide both sides by that term, so we end up having x1 equals to b f of a minus a f of b divided by f of a minus f of b. So this is the formula which we use to find out what x1 is going to be, to approximate what x1 is going to be. X1 is going to be equals to b, which is the upper bracket, multiplied by the value of the function at the a, minus a, which is the lower bracket, multiplied by the value of the function at b, divided by f of a minus f of b. Is this clear to everyone? Now, this way, us finding x1 like this, it doesn't really matter whether you use this expression to find x1, you use this expression to find x2, you use this same expression to find x3, and stuff like that. As long as you just make a small change. Here we've been very highly specific that this is the expression we use for finding x1. But if you make it, say, you're going to use this expression to find any guess value where the line cuts the x-axis, which we're going to call C. With bisection, we called such a point. With bisection, we're working out the midpoint. We're doing a plus b divided by 2. If you still remember with bisection, but with this method, first position method, we don't just say a plus b divided by 2. We make a slope, then where the slope cuts the x-axis, that is what becomes our C. So the difference with this method as much as it is a bracketing method, it is a bracketing method which also uses a method called the second method, called second, because the line which you have drawn, this line which we have drawn, this line which you have drawn, this chord, this is what in mathematics is referred to as a second. A second is a line which cuts a curve at two different points. Are we clear? It's a line which cuts a curve at two different points. So what we have used ourselves, we have used this line to approximate what the root is supposed to be. So whenever you draw a line, you can always find, you can always find what your root is supposed to be, what your guess root is supposed to be, by simply looking at what is the lower boundary, what is the value of A, what is the value of B, what is the value of A, and the value of the function at A, what is the value of B. So you can see here, what's happening is that our B is being shifted. After we find x1, okay, after you find x1, say, okay, fine, x1 is our new root, and the value of x1 is here. The next thing you do is you carry out a check between A and x1. Is there a solution to this problem? Does the function cut the x-axis between A and x1? What's the answer? Is it yes or no? Between A and x1, does the function cut the x-axis between A and x1? Our function f of x.
Yes, that's
It does, right? If the function cuts the x-axis between A and x1, then this is where the bracketing bit comes in. This B, which is your upper boundary, you squeeze your upper boundary so that it becomes x1. So that this becomes your new B. This x1 will now become your new B. Are we clear?
yes, sir.
In the bracketing method, we used to squeeze in the bisection method, we used to squeeze from both sides. You would squeeze from this side, you would squeeze from this side, depending on what was there. With this method, you primarily, most of the time, squeeze from only one side. So in our case here, as shown in this diagram, you will be squeezing from this side. So your B, which was your old B, is now going to become your x1. So your x1 is going to become your new B. So now you end up having a bracket which is between A and B, which is your x1 here. Then you work out a new value, a new solution, which is going to be your x2. When you work out your x2, fine, you found out what your x2, using that formula which we have obtained, you found out what your x2 is, or your new value of C. Then you ask yourself, between A and x2, does the function cut the x-axis? The answer is yes, because the function cuts here. So you squeeze your B now becomes your x2. Are we clear?
Yes, sir.
So again, you work out a new value of your root, which is your x3, or your new value for C. Okay, so you come to x3 here. After you find x3, then you ask yourself, okay, fine, this is what I've done. Does the function cut the x-axis between A and C, A and x3? Yes, it does. You squeeze again. So you can see there's really nothing happening this side. The A is not changing in any way. It's just there. But what's happening is that the change is happening only from one side here. As you keep on approaching, keep on doing that, eventually you're going to have a line which is going to cut here. Is that clear?
Yes, sir.
Yeah. So with this method, unlike bisection, you squeeze only from one end. Okay. So with this method, we're going to be working out our C, which is our guess root using this expression for x1. x1 is equals to b f of a minus a f of b divided by f of a minus f of b. So basically our C in general, generally our C, we'll be working out our C if we know what a and b are, as b f of a minus a f of b divided by f of a multiplied by f of c. Since this is a bracketing method, there will have to be some checks you have to carry out. So after you find your C, you have to check if a root exists between a and x1 or c by working out this product, f of a times f of x1 or f of a times f of c. If the product f of a times f of c is greater than 0, meaning that if the value of the function at a and the value of the function at c or x1 is greater than 0, then it means that there is no root which exists between that particular things. Okay? But if the value of the product f of a times f of x1 or f of c is less than 0, then it means that a root exists. If a root exists, then of course you proceed to do that. So in this case, if you work out the product f of a multiplied by f of c, if this is greater than 0, okay, if you work out the product f of a times f of c, then it's greater than 0. Then it means that between a and c, there is no root. So you make your a become c in this case, and you make your f of c become f of a. If the product f of a times f of c is less than 0, meaning that between a and c there is a root, then you make your c become b and you make your f of c become f of b. If the product f of a times f of c is equals to 0, then in this case you've got a root which is c. Okay, so basically this is the idea behind this regular force method. We have a way of, by selecting the points, the value of the function at this particular bracketing points, we can estimate what the guess value is going to be, and using that guess value, then we can start doing bracketing stuff. So we have to stop here. Over the past few days, I've been trying to work on an example, but the example I chose was very bad. It was taking the method a lot of time, a lot of iterations which had to be done. So I had to shift and eventually settle on a different method, on a different example, which I tried to work out yesterday a bit, but power went for most of the day. And also, the other thing I realized about this method, because I've never used it before, but I found that I think it's very useful. It can be faster than bisection. Since it's a bracketing method, bracketing methods are guaranteed to give you an answer. If you still remember what you learned last year, if you're using a bracketing method to find a solution, you're guaranteed to get an answer. But this method can be faster than bisection, but it also depends on what kind of function you have. Because sometimes this whole thing of drawing these lines, this thing can move very slowly sometimes. It can move quite slow, but you will not experience that slowness since you'll be using a computer to work out things. When it comes to doing things by hand, we actually try to make sure that this bracket A and B, when you're giving you a problem, which is what's going to happen, is as small as possible. So we give you a small interval. In this small interval, we want you to estimate what the value of the function is going to be. So when we meet tomorrow, we are going to look at an example. We have a class tomorrow, right? So when we meet, we're going to look at an example, and also on Monday. So I want to, depending on the method, I want to restrict ourselves only to a maximum of 2 examples. Then after each topic, the other thing which is going to happen is after each topic, you will get an assignment. This assignment has to be worked out. It's the only way I can make sure that you people are doing what you're supposed to be doing. You can write your assignment. I encourage you to write your assignment with pen and paper. Then you can scan your assignment. You can use an app called Adobe Scan. It's a very good app. That's what I used. Then you upload your assignment to Moodle. Then we can have a look at it. So these assignments will have to be uploaded, will have to be written and submitted as they become due, so that we are all moving together. Are we clear? I will not accept assignments which come at the end. You come with all your assignments, say, oh, these are my assignments. They will not be accepted. The assignments will have to be uploaded through Moodle. So I will only mark assignments which have been uploaded through Moodle. Are we clear? The labs, we will do our labs after we finish the renewable energy labs. But we have to see what happens this Friday, if there is still power, and also if I've been paid, because for me to do this internet stuff, I need data, and my data comes to an end on Friday. So if I've been paid by then, I can run around to buy data. But if I haven't been paid by then, or if there's load shedding, then we can't have anything. Okay. So this is where we end today. We are going to. Are we supposed to have class tomorrow? Or we have used up all our spaces?
I think the next class is on Monday.
Or the next class on Monday. Okay, fine. Then we're going to meet on Monday. But for this class, but there's a lab on Friday. Okay. So we got the lab on Friday. Then the examples for these problems, which means if it's on Monday, we have got a slot in the morning, you've got a slot in the afternoon, which means this bit, this chapter, since we're just looking at one method, we can finish it on Monday. Then after you finish it on Monday, you can expect your assignment. Then we move on to whatever chapter 2 is supposed to be. Okay. So see you on Friday and on Monday. The other thing is, this thing is being recorded. So of course I'm going to upload the recording to YouTube and also put the link in our Moodle. So you can check the Moodle for your course, for the notes. If you don't have the notes, you can look there. Okay. So see you on Friday and also Monday.
Thank you, sir.
Cheers.